Here we go, the floor's yours.
Thank you, Will, and thank you to BHS for hosting today's call, and welcome to all of you today, a special celebration via what's been a series of events and now a series of presentations of 10 years of the Cosmos UK National Soil Moisture Monitoring Network. I'm Helen Houghton-Carr from the UK Centre for Ecology and Hydrology, and I'm Project Manager for Cosmos UK. I'm joined online by some of my UK CEH colleagues, John Evans, who is Lead Scientist for Cosmos UK, Phil Vincent next to me, who leads our field team and the technical aspects of the project, and Magda, who is one of our speakers. And if I can just share my screen, hang on a minute. Sorry, Will, it says I can't share my screen.
Okay, no worries. Let me just double check that you have the permissions. Give me 2 seconds. Oh, that's why you're not coming up.
Well, we've got a good program of speakers, so
that should be okay now.
Okay. And I think I need to put that into presentation mode.
Click that one again, it should.
Which one? That one? Yeah. Sorry about that. I also apologise that me and Phil seem to be quite small in the camera. We haven't quite worked out how to zoom it in. If that's the least of our technical problems, that would be great. So, as Will said, we've got a programme of speakers. So, as well as my CEH colleagues, we've got Amir Badi from University of Lincoln, Yanchen Zheng from University of Bristol, and Patrick Stoll from University of Sheffield. Phil, next to me, and I will introduce the Cosmos UK network. And next, there'll be a series of presentations providing different perspectives on the importance of soil moisture information and applications of Cosmos data from the UK and around the world. And finally, John will close talking about accessing Cosmos UK data and taking a forward look. So our introductory presentation by me and Phil. I'm a hydrologist and science project manager. I started off in UK flooding, moved on to water resources in sub-Saharan Africa and parts of Asia, but have latterly returned to the UK with the Cosmos project and also the Flood and Drought Research Infrastructure project. My colleague Phil joined UK CEH from an R&D organisation which was looking at developing analytical instruments for the characterisation of nanomaterials. So Cosmos UK is a national network of near real-time soil moisture and hydrometeorology monitoring sites. Cosmos UK stands for Cosmic Ray Soil Moisture Observing System.
Sorry, Helen, sorry to interrupt it. We're not seeing your presentation. Your screen seems to be frozen on my end, and there's a few comments on not being able to see it.
Sorry.
Maybe if you try. Here we go. I can see it now. If some people in chat can just confirm that it's also working. There we go. Okay. Sorry to interrupt. I'll give it back over to you.
Yeah, sorry, when I did the test with Victoria, the screens were the other way around. So yes, Cosmos is the Cosmic Ray Soil Moisture Observing System for the UK, and a Cosmic Ray neutron sensor measures soil moisture over a circular area up to 200 metres in diameter. And there's a photo of one on the right there. The first site was installed in Oxfordshire at a place called Chimney Meadows in October 2013. So we're celebrating that site's 10th anniversary, and many sites have been installed since. The network currently comprises 47 operational sites, and there are 4 sites that have since been closed. The network is operated by the UK Centre for Ecology and Hydrology with funding from NERC, the Natural Environment Research Council, via capital funding and national capability. So on the right, there's a map of our sites. You can see there's UK-wide coverage, sampling a wide range of climates, topographies, land covers, soils, geology. There is a varying spatial density. Fewer sites in parts of the country where there is basically less soil and more rock. The hosts at our 47 sites comprise a range of different types of organisations, charities, environmental organisations, universities and other higher education institutes, local and national government, research centres and independent landowners. And where possible, we do try and co-locate the sites with existing infrastructure for research or environmental monitoring. Land uses at the sites also very variable: arable farming, livestock grazing, forest, grassland, moorland, nature reserves, and even a vineyard. So I'd just like to acknowledge our site hosts. We've got some of their logos here. We really appreciate the support that they give us. Some help maintain the Cosmos compounds, which is very useful. For a 10-year project, there's also been a huge number of staff at UKCEH involved, and I would just like to also acknowledge them. So thinking about soil moisture, obviously the wetter the soil, the more surface runoff you get, which could lead to flooding. The drier the soil, the more water farmers might have to use on their crops. So soil moisture information has lots of potential applications across a wide range of hydrology and other areas, and some of them are shown here. And some of the talks that you're going to hear today all refer to some of these applications. So now I'm going to hand over to Phil, who will take you round a Cosmos site.
Great, thank you, Helen. Okay, so for the next few minutes, I'll just run through a bit more about the technology that we employ at our Cosmos sites and in the Cosmos network. We'll do a bit of a dive into this Cosmos probe or CRNS tube that Helen referred to, and then I'll talk a bit more about the data and what we do with that once we've collected it. So the screen in front of you there, you should be able to see a snapshot of a typical Cosmos site. So this one is Balruddery Farm, just north of Edinburgh. And we've got a range of hydrological, meteorological sensors that we're employing to get a snapshot of the hydrological processes going on at that site. So starting at the bottom, we've got some subsurface soil sensors, so things like soil heat flux plates. We're looking at the soil temperature probes and the soil moisture in volumetric water content. These are point sensors, so we're getting quite a small volume measured there. Into the mast in the center of the image, we've got more meteorological sensors placed, so looking at temperature, humidity, barometric pressure. We also employ radiometers so that we can understand the net radiation hitting the site, as well as 3D sonic anemometer. We can use this for wind speed and direction, but we can also calculate the potential evapotranspiration using the tool as well. So the final sensor on that central mast is the Phenocam. You can see the image on the bottom left there taken from that Phenocam. It's a fisheye lens. There's 2 of them, one pointing south, one pointing north, and that gives us pretty much 360-degree cover of that area. It's used for understanding the phenology of the system, the surrounding environment around it, sorry. So this is understanding any long-term changes in land cover or land use. And finally, we'll come to the Cosmos probe. So you can see it kind of tucked away behind the solar panels there. And that gives us a calculation of the soil moisture in terms of volumetric water content for quite a large footprint that Alan identified earlier on. So with all of these tools, we get a pretty good understanding of the hydrology of that specific site in terms of moisture coming into the site, the retention of moisture within it, and then some of the exit routes as well. So now a bit more information in terms of that Cosmos tube, or the CRNS, or Cosmic Ray Neutron Sensor. This tool utilizes the basic principles around the reduction in energy levels of neutrons as they pass through our atmosphere and then into the surrounding environment. So to go into a bit more detail, cosmic rays are constantly bombarding planet Earth, and as a result of that, we get these high energy neutrons kind of raining or showering down onto our environment. As these high energy neutrons propagate through our atmosphere, they lose energy, turning into lower energy neutrons, and they're seen as the green segment of that energy spectrum there. Now, these low energy neutrons, if they encounter hydrogen atoms, they will thermalize, process called thermalize, where they'll drop to a kind of neutral energy state and effectively fall off that graph. If they don't encounter this hydrogen, then these low energy but fast neutrons will be scattered back out of the soil and detected by the CRNS probe that's seen there. The basic principle there being that the higher concentration of hydrogen within the soil, i.e. the more soil moisture there, the fewer fast neutrons will escape that soil and be detected by our cosmic ray sensor. So a few points around this. One of the real benefits is that it's not a point sensor. This is something looking at field scale, we're gathering neutron data from hundreds of meters kind of radial distance from the sensor itself. And the depth is going down from anything between 10 to 80 centimeters. These values will be dependent on the soil properties and the soil moisture at the time. The other thing to note is that there is a radial sensitivity to the neutron count as well. So the system is generally weighted towards detecting neutrons generated within the first tens of meters surrounding the probe. So with this tool, we get quite a good field scale idea of the volumetric water content contained within that site, and this we generate in near real-time terms. So that's a bit about the technology. Now, what do we do with all this data once it's generated? So there's a bit of a process box here. In terms of inputs, our main input is going to be the raw data coming through these sensors, telemetered across and saved onto a central server. But we need a bit more information. So we get the incoming cosmic ray flux from the Jungfrau, high altitude observation center. So this is giving us an idea of any kind of natural variations that there might be in terms of the cosmic ray flux hitting the Earth. We also need a bit more site-specific information. So every site is calibrated, and that will be based on the water retention capabilities of soil moisture at the time of sampling. In terms of outputs, I think we're very keen to share as widely as we can all of this data that we're busy generating. So we do a lot of exploitation and exploration of the data, and some of those talks we'll be seeing a bit later on. Annually, all of this data is uploaded into the EIDC database. So this is a central store of environmental data that we maintain. The information is further disseminated through our website, but we also have a lot of reporting that gets sent out. So We send out a regular newsletter, which you can feel free to sign up to if interested. But probably the key output is just the availability of this data to be used by any of the users in terms of analysis and research. This can all be freely accessed using our newly developed API, and I believe John will talk a little bit more about that later in talks. So that's pretty much it from me. I'll hand back over to Ellen.
Thank you, Phil. Will, do we have any immediate questions for me or Phil before we get on into more the talks more on the applications of the Cosmos type data?
I think I saw some questions coming in. Liv, do you have?
Yep, we do.
Oh,
so we've got 3 questions. So the first one is from Jane Allen. She's asking, are you doing anything to verify the rainfall recorded from the Pluvio rain gauges, which have caused some issues with data quality for the EA over the past few years?
Yeah, sure. So I guess independent of make or manufacturer, we try where possible to employ at least 2 rain gauges. At some sites we're employing 3 rain gauges. Measuring the amount of precipitation falling on a given area should be in theory quite simple, but it is notoriously difficult to do, and that's a very active area of research.
Yeah, John might come back to that when he's talking about his sort of closing and talking about some of the things we're doing, looking to improve the network going forward.
Then we've also got a question from Adrian Butler. The site you described looks very interesting. Are you able to give an idea of the installation and running costs of such a site? Of your example monitoring site?
I think a rough budget, and it varies depending on the site and the conditions and the host, but I think setting it up is about 2,500. Yeah. It's several thousand to set up a site. The running costs is mainly annual maintenance, responsive maintenance if any problems occur, and just a sort of preventative maintenance program to try and ensure problems don't occur. So it depends a bit on the reliability of the instruments at the site and the need to replace instruments that are becoming end of life or out of warranty. So it sort of isn't constant year on year. It depends where we are in the overall maintenance program.
Okay, brilliant. Thank you for that. We've also got one from Katya Petrova asking whether or not do you have detectors measuring counts within the thermal range as well as the red, green, blue that you mentioned?
Yeah, so the kind of bare Cosmos Cube, we use a moderated one, so that's where we're focusing on fast low energy neutrons. With some sites, I believe we do still have some bare tubes, but that's not a value that we include in our overall data set. I would say again, maybe John could correct me if not, but it's not something we share currently.
Okay. And then we've got Duncan Faulkner, who is asking, to what extent are the small field scale measurements from Cosmos representative of the catchment scale soil moisture?
That's definitely a John question, and I can see him grinning there.
Okay, yeah, that's a really great question. One that we're focusing on as we evolve our plans for floods and droughts research infrastructure. Very relevant in terms of planning new observations. I think ultimately comes down to your variability in the soil types across the catchment and variability in precipitation, essentially. So I think you've got to consider how representative your one field is with respect to other soil types and rates of precipitation across the catchment.
Okay.
And finally, we do just have one more. How many, this is from Helen Harford, and it's how many Cosmos sites would you like within your, would you ideally like across the UK, and do you have plans to grow the network?
But this is definitely something John will be referring to in his talk at the end, where he's talking about how we're using the data to try and map soil moisture across the UK. So if we could put that one on hold until then, and it's something we'll be coming back to. Right, well, I think we do need to move on because I'm going to stop sharing my screen. We do have 4 presentations coming up about use of CRNS data, this cosmic ray sensor data. And I'd like to start off by introducing Magda, who's a research associate here at UKCEH. She's a hydroclimate modeler, and her current work is focusing on application of soil moisture observations in drought evaluation and climate change, and she'll be talking about modeling future soil moisture using Cosmos data. Over to you, Magda.
Thank you very much for the introduction. Hopefully you can hear me well.
Yes.
So I'm just gonna share my slides with you. Can you see my slides? Great, thank you. Yes, so as Helen mentioned, I'll be talking to you about future soil moisture across the UK, and more specifically, I'll be talking about future soil moisture droughts at the Cosmos UK sites. And this is work that's been done in collaboration with Chris Huntingford, Elizabeth Cooper, and Jonathan Evans. And we're currently preparing a manuscript for publication. So there are many types of droughts, and specifically soil moisture drought refers to a period with very dry soils, which could be due to very low precipitation, intense but less frequent rainfall events, and or abnormally high evaporations. And any of these factors, or all of them, they can lead to reduced crop productions or plant growth. And specifically, we will be referring to soil moisture drought in the context of plant water stress. So I'll be using these terms interchangeably. And in the recent years, we already saw very exceptionally hot summers in the UK, and this happened, for instance, in 2018 and 2022. And the 2 plots at the bottom, they show our Cosmos data for northern and southern sites. And what's plotted here is a soil moisture index, where 0 indicates the start of the stress event, and negative values they indicate increasingly high intensity of the stress events. So here we see that in 2018 and 2022, the soil moisture index got very negative for a substantial period of time. And of course, unsurprisingly, soil moisture drought events they can have very negative. They can have many negative impacts. So they can lead to reduced crop yields, dry soils and vegetations, make it easier for fire to spread. Soil moisture droughts can lead to loss of grasslands, which will then limit food available for animals. They can lead to loss of natural habitats, which then can lead to loss of biodiversity. And dry soils, they may also intensify heat waves. So there are lots of things to worry about, and it's very important to be able to anticipate what may happen in the future. So, so how we look into the future? So to estimate soil moisture droughts, one of the ways to estimate soil moisture droughts is to estimate the future soil moisture. And to do that, one needs a soil moisture model combined with future predictions of the data that drives soil moisture processes. So what we do, we use the Joules land surface model, which we calibrate against Cosmos UK observations. And the way we calibrate it is by optimizing pedotransfer transfer function parameters. And pedotransfer transfer functions, they relate soil hydraulic parameters used by the model to easy to measure soil properties. So essentially, we optimize the soil parameters used by the Joules model. We then drive the Joules model with a very high resolution convection permitting UK climate projections. And that gives us daily modeled soil moisture in 3 time periods. So the historical period 1982-2000, near future time period from 2022 to 2040, and the far future time period from 2062 to 2080. And we get the soil moisture estimates at 34 Cosmos UK sites, and they represent a depth of 35 centimeters. And this is just a note that in the next slides, I'll be referring to the historical period as 1990, to the near future period as 2030, and to the far future period as 2070. So future soil moisture. So the plot here it shows our modeled changes of soil moisture for the 2 future periods with respect to the historical period, and we already see that in both future periods we see a decrease in soil moisture, especially in the summer and early autumn. And in order to analyze this soil moisture data in the context of soil moisture droughts, we first convert the soil moisture into the soil moisture index. And the way we do it is we use a fraction. We use a soil moisture index that refers to the fraction of available water for a plant. And this soil moisture index, it ranges between 5 and -5. Where 0 indicates the start of a stress, of a plant water stress, and the kind of increasingly negative values indicate increased intensity of the stress. So that's the soil moisture index. And then we use the soil moisture index to define drought events. So we define a drought event to start at a soil moisture index of 0. And we define and the drought event is defined by its durations and by the minimum soil moisture index that is reached during the drought event. And we consider 3 duration categories for the drought events. So 1 to 30 days, 31 to 90 days, and above 90 days. And we also categorize the drought events in terms of the minimum soil moisture index that gets reached. So we define moderate, severe, and extreme events. And this is a first set of results for the drought events. This plot is quite complex. But I'll explain it. It shows frequency of drought events average across all of our studied sites, and each subplot is for a different drought category, so moderate, severe, and extreme. And just looking at the kind of moderate and severe drought events and at the different time periods, it's not really clear what happens in the future in terms of how these events evolve. But looking at the extreme drought events, so the kind of the red plot, we see that in the kind of in the near and far future, the extreme events which have duration above 90 days, they significantly increase in the future. And I'm just gonna zoom in into this extreme drought events plot. And there's a dashed line here which separates 2 scenarios. So the first scenario is just the soil moisture output, just the modeled soil moisture output straight from the Joules model. And the kind of the scenario on the right there are drought events based on the modeled soil moisture, but bias corrected using the model biases that we see for the contemporary period, and it corresponds to the kind of to a wetter scenario. And both of these scenarios they show a significant increase in the extreme drought events above 90 days in the future. and approximately this increase is by a factor of 2. So that's the first result. Here I'm showing what happens at individual sites. So the maps here, they show frequency of extreme stress events above 90 days, and they show the far future period minus the historical period. So they show the changes in the far future period. And again, we have these 2 scenarios, without and with bias correction for the soil moisture. And again, in the first scenario, we see, so the bigger dots, they correspond to bigger correspond to increases in drought events. And there are lots of sites, pretty much all of them in the first scenario, that see increases in this extreme stress events above 90 days. In the second scenario, it's slightly less so. It's a wetter scenario, but nevertheless, still many sites show these increases in the drought events. So that's what happens at individual sites. And then finally, I just wanted to show you what happens in individual months. So these plots, they show a probability that a majority of a month experiences severe or extreme plant water stress, and that's for these 3 time periods. And here what we see is that in the near future, we see that this probability increases for months between June and September for both of the scenarios, and for the far future, this probability increases between May and November. And again, this kind of this increase of this kind of severe drought period may be of significance for the agriculture, as there's kind of a range of months, that there's quite a range of months there, which may affect different development stages of the crop. In summary, we produced estimates of soil moisture for 3 time periods at 34 Cosmos UK sites. We did it by driving the JOULES model calibrated against Cosmos UK observations with the very high resolution UK climate projections. And on average, across all sites, we see increase in the frequency of extreme plant water stress events of duration above 90 days. These increases are visible across all or many of the Cosmos UK sites, depending on the scenario. And for individual months between May and November, we see increased probability that these months will experience severe or high stress in the far future period 2060 to 2080. And thank you very much for listening, and I'll take questions if there are any.
Yes, we've got a question again from Katia, if that's okay. And she says, great presentation. Thank you very much, Magda. Looking into JOULES, what is the minimum grid size of the model? Also, is it freely available or an open source model?
So we run JOULES in the kind of point at a point mode. So I'm not sure if I can comment about the grid size question. So essentially, yeah, we run JOULES at a point. And what was the second part of the question?
Is it a freely available open source model?
Well, you have to be a member of a research institution, and you have to apply for access to JOULES. But as long as you kind of meet this criteria, you can. Well, I think. Yeah, you kind of have to justify why you need the JOULES model, but it's, yeah, you can, if you're a member of a research institution, then you can have access to it.
Okay, so apply for access, yeah, and criteria for that. And just one question from me, in terms of you've looked at historical soil moisture stress. Have you actually at any point gone back and looked at whether or not there's data from the farmers or the landowners? Have you gone back and looked and said, looked at patterns in crop stress and yield to compare those against the historical soil moisture deficits and droughts that you've looked at? Just out of interest.
Yeah, so what we did, because we calibrated the model with our Cosmos observations, we evaluated the model against our Cosmos observations, so against the Cosmos soil moisture data.
Yeah.
And there we kind of calculated biases.
Okay.
And in our results, we kind of produced two scenarios. The first without bias correction, and the second with bias corrections. So we included that kind of uncertainty for the UK climate projections. After running the JULES model, the UK climate projections, we produce data for this historical period between 1982 and 2000. We've not collected any data for that period, but we did bias correct the UK CP18 data against CHES gear data, which is kind of gridded data based on observations. But we didn't do any specific checks at particular, using historical data from farmers or landowners.
Okay, thanks very much for that. I appreciate it. Okay, that's all of our questions. Thank you, Magda.
Thank you.
Yeah, thanks, Magda. So next we have Dr. Amir Badii, a senior lecturer in sustainable energy from the University of Lincoln. And he's worked on several collaborative projects with UKCEH and the Lincoln Institute for Agri-Food Technology, where he was involved in developing an autonomous Cosmos rover for measuring soil moisture in farmland. And that's what he'll be talking about. So if I can hand over to you, please, Amir.
Great. Thank you very much, Helen, for the introduction. I hope you can hear me well and you can see the slides. Can you?
All good.
Okay, great. Fantastic. So in the next 10 minutes, I'm going to talk particularly on one project that we did with UKCEH. Simon Pearson, myself, Jonathan Evans, and their team were involved in this project, and we were looking into using additional moderator to control the footprint of Cosmos rovers. So the aim of this study was to show the feasibility of using cosmic ray neutron probes, CRNPs, to map moisture content of agricultural lands. And the purpose of it was really to enable farmers to more efficiently irrigate their farms by having a moisture map of the field prior to the irrigation. But we really needed to shape the footprint and limit the footprint and to have more control on the footprint of the detectors. Helen, at the very beginning, mentioned that the probes can, their view is around 200 meter in radius. We needed to bring it down to have a more resolution and to have a better moisture map of the field. So the solution that we have and the approach that we took was to use a robotic platform. But also, instead of installing a single probe vertically, we had 12 different detectors, 4 in each box, which were placed on a robotic platform horizontally. In order to bring down the footprint, we used 5 centimeters of high-density polyethylene, HDPE, and we covered the top and the sides of the detectors in the box. So the purpose was, the reason that we used polyethylene was mainly because there are 2 types of passes that neutrons travel until they reach the detectors. The blue line represent the neutrons that they almost immediately after exiting the soil, they enter the detector, they hit the detectors, they travel a shorter distance, and we wanted to focus on the blue lines on the shorter path. The other paths, the green one and the red one, they were the neutrons that they were traveling a longer distance, having more collision with the water molecules in the soil and environment before hitting the detectors from the top or the bottom. Putting the HDPE on top and sides of the detector really was to suppress the path of the green and red lines, these two lines, and simply by stopping the neutrons entering the detector and hitting the detectors from the top. So that was the aim. We wanted to focus mainly on the blue one, and we wanted to suppress the red ones and the ones that they enter from the top of the detector boxes. So the robot platform that we used was a modular platform by Saga Robotics. We worked with them on different agriculture projects, and we used this modular robotic platform for different projects. In this particular one, we decided to place the HDPE and the detectors on these robotic platforms. If I can go back. So as I mentioned, it's modular, so the size can change. The robot has the capability to be autonomous. However, in this project, we were using a controller to have more control on the movement of the robot, and it also enabled us to be in the safe distance from the detectors, not to introduce noise to the results. The battery of the platform, the robotic platform, could work for 10 hours, depending on the load and depending of the speed or the acceleration. That we didn't really need high acceleration or speed for this project. And it was really maneuverable, so it made us really easy to maneuver in agriculture fields. We have used the detectors and the robotic platform on different agriculture fields and even not agriculture fields. So we started with a Lincolnshire heritage airfield, which was an old airfield. It included a large area of concrete and a large area of grass. We had the actually pleasure to meet the Lancaster, two different generations of robots in a sense, Lancaster and other robot. As I mentioned, the large concrete area enabled us to really gave us the access to a dry area, and the grass area gave us access to wet area. And to really test the footprint of the detectors, we started from the dry area, moved towards the wet area, the grass area, with more resolution as we got closer to the grass. You can see we even had a reading at the border between the grass and the concrete area to better understand the footprint of our system with and without the moderator, which was HDPE. So you can see a very slow movement of the robot to make sure that the noise that we introduce system is minimized. Then we move to a stubble field in Lincolnshire. We made a grid of different points. The distance of the points was 60 meters, and we started to make readings at each point in 3 different weeks. So the first week we had a clear sunny day. During the whole week it was quite warm and sunny. So when we moved again to the field in the week after, we had a full dry week. So we expected that the detectors are going to detect the moisture level, which was lower than the previous week. And we returned to the field in the 3rd week, and we were lucky because during the 3rd week it was quite rainy. So we had 3 different weeks with 3 different moisture content soil. and we were hoping that we can capture that moisture content correctly and make a moisture map of the field. As you can see, 3 different weeks. A is representing week 1, B week 2, and C week 3. You can see from the legend that they are quite different moisture level. We have lower moisture level in the 2nd week, as we expected. It was a dry week, and we had higher moisture level in the 3rd week, which was quite wet week, and the detector and the system could capture that change in the moisture level of the soil. We also had TDR readings, which are point-based reading for each point, and we wanted to compare TDR reading, which is a point-based, with our system of the rover. As you can see in the results, again, week 1, week 2, week 3, as it's demonstrated as ABC, quite close, although there are some discrepancy at some points, and it is very much dependent on the moisture content level of the soil, the compactness of the soil, and also the TDR. We use 7.6 centimeter probes. It would have been a different reading if we had longer or shorter probes, which was another downside of the TDR point-based readings. So I'm going to wrap it up here. I would summarize by saying that the additional moderator could successfully reduce the footprint. For example, for volumetric water content of 20% and atmospheric humidity of 10 gram per cubic meter, the footprint was reduced from 63 meter without the moderator to around 16 meters by adding 5 centimeter of the moderator. However, it came at a cost of considerable reduction of detector efficiency, as you can see in the graph. So the other conclusion is that to be able to use the system, rover-based CRMPs in agricultural lands, and to create agricultural lands moisture map, more research really needs to be done in different environments, different climatic conditions, and different soil type to really make it an effective one. The whole data, a lot more than what I presented, are in our paper that we published with the CEH and also University of Bonn and University of Arizona. The QR code should hopefully take you to the paper if you are interested to learn more about the project. And that's pretty much everything that I want to talk about. Happy to take the questions.
Hi, Amir. Thanks for that. Does anyone have any questions? There's none in the chat box, but if you'd like to put a question forward, we've got time now. No, no questions after that presentation.
I might have a question.
Oh, there we go.
Amir, so a great presentation. I totally like that. I was wondering, it looks like you have just sitting around and then you move it again and it's sitting around. So I was wondering, the roving seems like, do you have any data sets where you just use the robot for actual roving instead of stop and go and see how it performs while moving?
We didn't collect any data while we were roving. We needed to stop at each point for half an hour to make sufficient reading so we can have meaningful VWC, volumetric water content reading. If I correctly remember, the work goes back to 2017-18. We gave it a try to collect reading while we were roving using the lowest speed possible on the rover, but it didn't give us enough neutron counts to be able to have meaningful volumetric water content conversion.
Yeah, what was, I mean, I might have missed it. What was the performance? What was the power, the counting power per hour in counts per hour from the system that you used?
I don't have it on top of my head, but I can check it and come back to you. If you would like to drop me an email, I can respond to that. I don't. Maybe I'm not sure if we can or not, but John might be able to advise. We can share some data, some of our readings, or so that's absolutely possible.
No, I mean, the thing is that I was just wondering if you could increase the performance of the sensor, you might be able to. I mean, I find it super cool, this robot thing, and it might be able to just using data kind of on the fly as a roving system when you have a higher performance.
As you notice, we use 12 detectors on that pack. So we kind of try to improve the efficiency, but by increasing the number of detectors rather than individually improving the detector. But if that would be possible, then it even reduces the weight on the robotic platform, which is an advantage.
Okay, thanks so much. Great.
We've got 2 more questions that have come in. We've got one: would you be able to use a similar approach to look at the impact of trees on soil moisture?
Interesting one. I'm not sure. I don't know the short answer. John, would you like to comment on that?
Well, I suppose if you're thinking of the actual impact of changes in soil moisture around tree roots, then I guess in principle, yeah, you could do that. If you've got, you still might find even with 16 meters kind of spatial resolution that you might be too close to neighboring trees. So there may be better ways of doing that. But the trees themselves, the water in the trees, biomass water, will also have a sort of a complicating effect, let's say. But you might also be interested in that biomass water. So I'm not quite sure which aspect you're most interested in.
We've also got another question, which is from Rob Soley, and it's: do farmers have any kit at all which they put on a tractor to check soil moisture as they drive, or is that pie in the sky?
I don't think they have access to such tools. I think the most common way of measuring the moisture is using techniques like TDR, point-based techniques. So yeah, this was kind of an innovative approach that probably, if it works and it is proven, then it would have been offered as service to farmers. I think that was the idea. Again, because John was very much involved, I would go back to him. Any comments on that, John?
Well, I think I would just say more generally that there's a lot of development going on, as we'll see from Patrick's upcoming talk on new detector technology, and yeah, hopefully there'll be more sensitive detector packages at a more affordable price point to enable that sort of application to be possible.
Yeah, I'm afraid we really need to move on. So perhaps John and Amir, you can have a look at questions in the chat and address any that have come in. So scale next from the UK to the globe, and I'd like to introduce Dr. Yanchen Zhen, a research associate at the University of Bristol. And she is going to be talking about evaluation of soil moisture products using CRNS observations across the globe. Over to you.
Yeah, hi everyone. Thanks for the introduction, and I hope you can already see my screen and also hear my voice. Okay, cool. Thank you. Hi, everyone. I'm Yan Chen, and I'm a postdoc from University of Bristol. And it's really happy I can share our work about evaluation of the reanalysis soil moisture product using Cosmos Ray neutral sensor observation across the globe. As we all know, like soil moisture can have like influence on a lot of physical process in hydrology, like evapotranspiration and infiltration. And so the accurate and robust soil moisture estimates are quite important for our research. And in my case, when I was doing my PhD, I was trying to develop a flat estimation method for the UK, and we found soil moisture play an important role on that. So we trying to use find some product to use soil moisture as one of flat like predictors, and then we find there are so many soil moisture products available, and we don't know like which one is the best to use. So, and one day, one of our PhD student, Daniel Power, he is giving a talk to our group, presenting about his newly developed Cosmos Ray neutral sensor pattern tool. And that's how I find these great CRNS, like soil moisture measurement techniques. And I also find our nicely Cosmos UK dataset is also available, and also some data from other CRNS network. So this is how we get.
Catherine, sorry to interrupt. Could you change to presenter mode, because we can see your desktop?
Let me just resharing it. Is it better now?
Yeah, thank you very much.
Okay, sorry about that. So our aim is to evaluate the soil moisture product against the CRNS dataset. And the reason for why we choose to evaluate for the reanalysis product is because it normally have long-term records and also the global spectral coverage. As for the hydrology, it's quite important to get soil moisture at quite long-term records, like at the same time period with the stream flow data. And the reason why we use the Cosmos Ray neutral observation is because like these techniques will give us field scale measurement. And actually most soil moisture product evaluation working before is actually against the point scale into soil moisture measurement. So it's definitely better we use the field scale measurement to solve the spatial scale mismatch problem. And our research aim is to provide guidance for the researchers on choosing the soil moisture product, and also provide some insight on direction how to improve the soil moisture product for the product developers. Sorry, just. Sorry, I just have some troubles changing slides. And hopefully you can see it now. Sorry about that. And in our study, we collect a total of 135 CRNS dataset across the globe. And as you can see in the map, our sites have across different climate region and also the land cover type. And our sites is mainly from UK, Europe, USA, and Australia. So actually different CRNS network, they are using different nutrient correction methods. So that would lead to different soil moisture values eventually. So as I mentioned before, Dan Power from our group, he has developed a crisp pattern tool so that we can precise all the CRNS data in the same way and to use the harmonized global observation for the evaluation. And also our colleagues, Rafael Razalim, he has been leading the establishing of the global Cosmos network and also the harmonized data set. And hopefully our their paper and also the data set about this will be come up soon. And if you would interested to know more or you want to collaborate or contribute, you can contact Rafael about that. And as for our reanalysis product, we evaluate 7 products, including CRS version 2, GLDAS, CRA40, ARA5 Land, Marine 2, GLI, and also the GRA55. And these products actually have cross different temporal, spatial, and vertical resolution. So we present several solutions for solve this scale mismatch. As for the temporal resolution, we aggregate all our reanalysis data to the daily scale. And as for the spatial resolution, we individually calculate the statistic metric for the multiple CRNS sites that are located in the same grid. And for the vertical resolution, we use the revised weighting function to assign a weight to different soil layers data and to finally calculate the weighted average of soil moisture data for comparing with the CRNS dataset. So we actually precise all the reanalysis data in the same way and also for comparison against the observation. And here is our results. We use 6 widely used statistic metrics, including R represents the temporal correlation for the whole soil moisture time series. And we also compute the time series in the seasonal cycle and anomaly series and calculate the temporal correlation for those time series. And also the mean square error, the unbiased root mean square error, and also the bias. So basically, all reanalysis products exhibit good temporal correlation with the measurements, and the R value spanning around 0.69 to 0.79. But if you look at the specific metrics, actually the results can be different across different regions. So in the below reader plots, it shows the performance for each metrics and for different region. And also the colored line in the figure represents different reanalysis product. If the larger value on the radar plot or the further away the line on the radar plot from the center, it means the performance is better. So if we only look at the figure A for the UK, the gray line has further away from the center, and this represents the CFS version 2, which means these products have the best performance in terms of the temporal correlation. And if we look at metrics in the Europe, then actually the orange line, which represents the ARA5 Land, this one will give the best performance for the Europe. So these radar plots actually summarize a lot of information, and we hope the researchers can choose their own products and base their own needs. And we also have the results for the US and Australia in our paper. And also because our sites collected are actually across different climate and land cover types. So we also trying to explaining why these reanalysis data have differences in their performance. So for example, for the climate, we classified our sites into different groups like humans, balanced, and arid clusters, and then we calculate the median matrix value for each group and also for each product. And we find that the reanalysis product tend to overestimate in the arid climate and underestimate in the human region. And for the land cover, we did the same thing, and we observed that the low performance is always found in the shrubland. And for our the final slide, we summarize the recommendation for choosing the soil moisture product based on our results. All these rankings are calculated based on the Bronc ranking method and according to all 6 statistic metrics and all available sites. And we also classified the results into 3 different categories, like optimal and okay and least. So as shown in the table, but please note that actually the differences between the median value of the matrix across the products is actually quite small. So for example, if you're looking forward a soil moisture product for your research for the UK, then we recommended the CRF's version 2, and GLIM is the best one for use. And if you want to have a soil moisture product for global analysis overall based on our results, we would recommend that you use like CRA 40, GLIM, and ARA5 Land, and CRFS version 2. So this work is already under review in the HAS paper. So if you would like to know more, you can using this QR score to have access to our paper. And that's all for me. Happy to take any questions.
Very much for that, Yan-Chen. Can I ask if there are any questions? We don't have any in the chat box. Anybody? No, I don't think so. Thank you very much for that. That was a really interesting
thank
talk.
you. Thank you, Yan-Chen. Anybody thinks of any questions after absorbing that, they can stick them in the chat and Yan-Chen can have a look at them. So our final application speaker is Dr. Patrick Stoll, who's a lecturer in particle physics at the University of Sheffield. And his research interests include development of low-cost radiation detectors and Internet of Things sensing systems for irrigation management. And he'll be talking about a project in Brazil.
Okay, can you hear me?
Yeah, that's it. Thank you.
Yeah, you can see it full screen, yeah?
Yes.
Okay. Okay, so thank you for having me. I'm Patrick Stoll from the University of Sheffield. I'll say at the very start that I'm not a hydrologist. I'm actually a particle physicist, as they mentioned. And my area of sort of interest in all of this is actually on sensor development specifically, and also interfaces to sensors. So what I'm going to talk to you about today is I'll get on to how we are looking at cosmic ray sensing in agricultural sites in Brazil. But just as a sort of introduction on how we got here. So I just recently finished a research fellowship at the University of Durham, specifically looking at alternative technologies for neutron sensing for the cosmic ray sensing technique. So right now, you know, CH uses, I think, correct me if I'm wrong, but boron trifluoride neutron detector systems, which are gaseous neutron sensors. So the way these work is that when a neutron comes in from a cosmic ray, they actually go on and interact within the boron inside a detector, and these then actually produce charged particles which we can detect. So we don't detect the neutron directly, we detect these extra charged particles that are produced inside a sensor. But that is actually just one type of neutron sensing technique. There have been lots of developments in the nuclear sector the past sort of 30 years, looking for alternatives to helium-3 or boron trifluoride neutron detectors. And there are two sort of types we're exploring at the moment. There are foil-based sensors, where instead you actually put this sort of boron compound on the outside of a tube, and it creates the charged particles when we pick it up. Or the one that I'm actually specializing in is what's called a scintillator. And what scintillators do is when charged particles are produced inside them, they actually generate flashes of light. So we have pretty much these very sensitive cameras almost, but they're just a single pixel. And inside them, when a neutron interacts, we get these pulses, which we can actually tell from background. So I had a fellowship at Durham where we looked at building some of these scintillator-based detectors. And actually in 2021, thank you to Jonathan Evans, we actually deployed some of these next to one of the Cosmos sites at Cockle Park and showed that we could see a sort of the relative change in neutron rate over time was consistent with what was being seen on the boron trifluoride systems at the Cosmos site. After that, we worked on reducing the cost as much as possible for these sensors. And then we started asking the question, well, if we actually wanted to deploy these in agriculture, how would that work, right? How can we have farmers run these things in an almost plug and play fashion? And we started looking at different ways to use sort of Internet of Things sensor processing to take the data in real time, extract soil moisture, but then actually look at how that data could also be used by farmers. And that led us to work with some colleagues in Brazil who developed this platform called Swamp. They developed this in 2018. It's an attempt to look at a smart farming solution for data-driven irrigation. So the idea is you don't just use sort of models to estimate how much water you need to put down for irrigation, but you actually continuously take data as much as possible across a field. And that data then provides information on how drainage might change at different areas of your site, how the crop is affecting drainage and stuff like that. And it tries to automatically update what the irrigation prescription is. So the idea is raw sensor data arrives, it arrives in our actual raw database, and then that triggers this automated calibration which extracts the volumetric water content, either using more traditional probes like capacitive probes, but also we have techniques for neutron probes now. It then uses crop simulation models to try and estimate what the optimum irrigation prescription might be, and then tries to predict what effect that might have on the yield. So it gives sort of different ranges on if you irrigate a lot or on a small amount, what will the effect be? And it does that, passes that all back through from the very start of the crop simulation as well. So what we can actually do with this platform that we're developing is simulate crop growth, the effect that has on soil moisture, and then actually feed that back in to simulate raw sensor data if we want. So we can actually optimize things like placement of cosmic ray neutron sensors on sites. This plot on the right-hand side here is actually simulated cosmic ray neutron data that's been used to extract, reconstruct the soil moisture for some crop simulation. And it includes all these sort of standard effects of cosmic ray sensor. So statistical noise based on how long you're integrating your counting period for, and pressure corrections and things like that you need to apply. So the idea is we're trying to make a sort of end-to-end processing chain which allows farmers to literally just drop these things in the field, and it should try to estimate irrigation practices from that. We had an initial trial last year working with Raphael Rossolum and Dan Power at University of Bristol, where we deployed actually some low-cost cosmic ray probes at next to one of their cosmic ray sensor sites. And then we developed this Crispy server package, which actually is an extension of code that Dan Power had already written, which actually generates this nice API that you can just fire raw cosmic ray neutron data to, and it will try to figure out how to extract the volumetric water content from that automatically. Because the idea is, if you're setting up a smart farm, a lot of the information you might need to make these corrections to get at the true water content from cosmic ray data, you might already have. So, a lot of smart farms do sampling of soils to understand porosity, density, and things like that. And these can kind of be loaded into the calibration methods. And then we came up with an automated way to actually do the calibrations themselves so that you can literally try to just drop these probes in the field, and they'll try to use as much data as they have available at that time to come up with correction constants that they need to extract the true water content. And the reason for that is actually when speaking with farmers and getting out in the field and deploying these, we found when we were working on trying to put sensors in the middle of heavily managed sites, we actually had a lot of issues where sensors had to be moved or dropped down and then put in different locations based on what their farm operations were doing. And it made it a little bit difficult. So at the moment, we've moved to the system where the way the platform works is it queries all possible information at any specific point in a field and tries to use that to both extract the calibration procedures for Cosmic Ray sensor probes, but also all the weather data and things necessary to extract soil moisture and separate it out into different management zones for a field. So following on that, we've actually moved now to testing these systems actually in Brazil. We had a first pilot at Lanapra, which is a precision agricultural facility in Sao Paulo state. And here we've just been testing the ability to actually combine different types of neutron sensors within this platform, as I said, in a plug and play fashion. So we had one of our boron nitride scintillator probes that's on the left-hand side of this plot, developed at Durham University. And we deployed that actually alongside an alternative gaseous foil-based detector from Stix Neutronica, which is an alternative neutron sensor manufacturer in Germany. And they've kind of been involved in this project and supported a lot of the work on sort of processing development. And we deployed both of these at the facility mainly just to show that we could, literally plug them in. They would start sending data and we could track all the different sensors within a single platform. And alongside these sensors, we actually deployed arrays of in-ground capacitive probes. And again, it is a system where you just put these things in the ground, they can immediately start sending data and everything's geotagged and located. So you can start to build up site-wide maps of soil moisture in the space of sort of a day or two. Following on from our Lanapra sort of hardware testing, we've now moved to 2 real pilots on agricultural sites in Brazil. We have one in Goiás State, which is working with another agriculture institute in Brazil, Embrapa Rice and Bean. And they have this area where they have one rice paddy field that's actually on the north side of the site. And then actually right next to it is a cattle area where they just have livestock grazing. And we've got 2 sensors in here. Actually, we're looking at seeing how they can monitor differences in drainage across the 2 sites and link them to land management practices. And then we have our main pilot, which is actually working with a real farm in Brazil that uses center pivot irrigation. And they actually are looking at whether they can move to variable rate irrigation in the future. So this is where you can actually divide the field into many, many different zones and apply irrigation differently within each zone to try and maximize your yield. So on that site, we have 4 of our Cosmic Ray probes, scintillating probes deployed. The locations of these shown on the left-hand side image. So we have one in the center. We actually have one here, this D site, which is a region of the field they know drains a lot quicker than the rest of the field, and they've seen changes in the yield maps for this area of the field. And in contrast, we have another sensor at site E here, which is a region where they know is prone to flooding. And again, they have differences in the yield in this region of the field as well. So we can directly make these comparisons between how different areas of the field perform and how our platform as well is able to pick up on changes in drainage rates just by using this data-driven modeling system. And then additionally, the thing they've been most excited about is we have some probes actually fitted to this irrigation arm itself. So you can see, I'll show you some pictures in a minute, but you can see this center pivot arm. This swings around the field and irrigates the entire site. And we have some probes actually mounted to those themselves. And this is really the big thing for them, because then they don't have to worry about probes being lost or them having to be pulled out and reinstalled during seeding and things like this. Instead, we can just leave the probe on there and it can sweep around the field at different positions and try to monitor soil moisture. In addition, we actually have one of these big green tubes here. So the total sensors we have are these blue sticks that are the scintillator tubes that were built at Durham. These capacitive probes that were built in Brapa, which actually measure soil moisture at various depths below the surface. And then we have one of these large STIX Neutronica systems that I showed on the previous slide, which is also going to be deployed in the center of this pivot site in the future. So this is the actual site itself. You can now actually see the irrigation arm. It sweeps out over 500 meters of the field. And as I mentioned, we have these sort of static probes that are deployed at various locations. And this roving probe, which is actually GPS tagged as well. So it continuously sends data. Actually, it sends counting rate information every 15 minutes, as well as its position, so that when they sweep this thing around the field, we can try to build up variations in the soil moisture over the entire site. And the entire thing is all connected to this Things network LoRaWAN interface to this gateway in the top right-hand side. So it is really the system that you just put this gateway down in the field, and then you can put these probes anywhere, and they can transmit data up to 10 kilometers away and send it all over a 4G communication protocol. So you can sort of, the idea we're working with the farmers is that they can put sensors down where they think they would be best placed, but then if they want to verify the response to sort of irrigation in different regions of the field, they can look at actually picking sensors up and moving them and taking a short calibration campaign of just doing soil sampling around the sensor that day before it immediately can be loaded into the platform and stop being used for soil moisture estimates. So that's it from me. So our goal for all of this is to try and make the technique as easy to use for farmers as possible. We're about to actually publish the full platform we have in a few weeks, and that basically allows you to just fire up a server that you can send raw cosmic ray data to, and it tries to get as much information as possible from things like weather services, weather stations you've installed, and soil information, and use that to extract cosmic ray volumetric water content estimates. And then the follow-on work we have for this is really looking into this. We have this interface where we can run Python. We use an interface called the Python crop simulator, and we can run that and actually predict crop growth under various irrigation situations. And the next stage of this is really working with the farmers to show that that can be used to optimize crop yield based on different irrigation plans. So if there's any questions.
Patrick, there's one question from Katia, and it was, what was the approximate cost of building one of the scintillator sensors?
So we pushed it down quite a bit. We now have, we can build one scintillator probe for around £450. That doesn't have the sort of usual associated markup and overheads for setting up as a company. But we are actually now in the process of trying to set up a serious supply chain. So there are companies that have looked at these scintillators, buying them directly from the nuclear sector, but they can still be quite expensive. So their systems can usually be on the order of sort of £6,000 to £7,000. So we're looking at actually in-house manufacturing of this scintillator material. And we're hoping to sort of hit this ballpark of sort of £400 to £500 purchase price eventually.
Great, thank you, Patrick. We're sadly approaching 2 o'clock. Sorry, it looks like we're going to overrun a bit. So I'm going to hand over to John Evans to give the final presentation. John is a hydrometeorologist specialising in application and development of cutting-edge observation techniques, especially around CRNS techniques for field scale measurement of soil moisture. And he's been technical with Cosmos UK since it started. Thank you, John.
Thank you, Helen. Just get that into full screen if I can.
Glad it's not just me who gets it on the wrong screen.
Sorry, I don't know why that's not working either. So, I think I'm going to have to stop sharing it again to get it to work. Sorry.
Yeah.
Okay, is that better? Can you see that as full screen?
Yeah, that's
Yeah,
better.
yeah, great, thank you. Okay, sorry about that. Okay, so I'll try and run through this in maybe 2 minutes. I'll skip the introduction and go straight to how you can access Cosmos UK data. So firstly, we have our Cosmos website, the address there, cosmos.ceh.ac.uk. There's lots of information on there, including live data plots, but also information about each site, metadata and photos of sites. So that's a really good place to start to explore the types of sites we have, and just to look at some of the live plots on there. If you want particular data sets, you can now download those yourselves on demand, and that's the QR code there, and I'll show more of that in the next slide. If you wish to use a data set with a published DOI, you can download that from the Environmental Information Data Center. And there's data there until the end of 2022, and we update that annually with a new DOI. And if you prefer to access data via code and pull it straight into a model or other application, you might want to update it regularly. For example, we have an API now available, which is also explained on our website. So the most useful thing I feel for most people to access data is this new on-demand data form. Again, you can get to that using the QR code there. It's on our website. Scroll down the page, you'll find this data form. Just ask for a little bit of information about yourself and your organization and the application, just for our records. You can then select which sites you want data from, or you can select all sites. Just be a bit mindful that obviously the larger the request, it can slow down our server a bit. And at the bottom, you can select either daily or sub-daily data. When you select sub-daily, you'll then get a list of variables you can select from, or again, select all variables, including data flags, and you can select a data range, a time date range at the bottom there. When you submit the request, it's an instant system. It uses the API behind this form, and you should see data download immediately into your browser downloads folder. So that's a really good way to quickly get a data set, and that's up to the previous day's data. So moving on to future outlook very briefly. So we mentioned earlier, I think, mapping soil moisture at the national scale. So this is something we're working on to produce a 1 kilometre soil moisture map, sort of calibrated and informed by Cosmos UK data, obviously using lots of other driving data and soils information across the UK, as well as other data such as soil carbon information. I'll show you an example of that in a moment, but that's coming on quite nicely. It's just always a bit challenging to produce it in near real time and have the driving data available to run it. There was some discussion or mention earlier about where we locate stations, and we will be reviewing the network coverage with regard to how well it captures the UK's spatial and temporal soil moisture dynamics. So that, if you like, can be network optimization. We may consider reducing the size of the network to reduce operational costs as well, but hopefully we can do that in a way where we don't lose important information. And we already are measuring components of the surface energy balance, sensible heat fluxes, soil heat fluxes, and net radiation. So we have, as the residual of the surface energy balance, a good estimation of actual evaporation, and we haven't really published that data properly yet, and we hope to get that all up to date and published next year, early next year, hopefully. We are looking at some of the technical issues kind of fundamental to the technique. We have to compensate for changes in incoming neutron fluxes, and these can be influenced by things like the 11-year solar cycle, and we suspect this can be a cause of some drift in our data. We're also engaged in a European metrology project through Euromet, which is the Association of European Metrology Institutes, and looking at standards for multi-scale soil moisture monitoring, and also harmonization of data collected at different scales, whether that's a point scale, field scale, or more like a satellite scale. And you can read more about that at the project homepage. And the last kind of point of information really is that there is a workshop on cosmic ray neutron sensing technology, CRNS24 International Workshop in Hillsborough, which is one of the Cosmos UK host sites run by AFBI in Northern Ireland, County Down. That's the 24th to the 26th of September 2024. So if you're interested in the CRNS technology, do save those dates, and there'll be information on the AFBI website from January as to how to submit abstracts to that. So I'm just going to close by showing you an example of our 1 kilometre soil moisture map. And this is just running for 2018, showing some of the drought. We haven't yet run this for 2022, but obviously it'd be great to do that. But this is looking like a promising product in reflecting soil moisture across the UK and producing reasonable values for that. Obviously, validating it is quite challenging. Yes, so the important thing is we're actually using a machine learning approach here rather than a process-based hydrological model. So I'll just close with that and thank everyone for a really great range of talks today.
Thanks, John. Are there any final questions for John?
There's one, and it's just, is the data platform, sorry, is it possible for the data platform accessing the CRNS calibration NO data? Is it possible to access that platform?
It's not directly available via the API, but you can contact Cosmos UK at ceh.ac.uk. We're happy to make that available. We probably need to explain how we we calculate the N0 data in our network so that you can interpret it correctly as well.
Great. Well, I shall just wind up here then. So apologies for overrunning. On behalf of the Cosmos UK team, we've been thrilled to have the opportunity to mark our 10th anniversary in this way. And a huge thank you to BHS for hosting us and to all of you for participating in the event. Also, a huge thank you to all our presenters. Can we give them a big virtual round of applause, please? I think you can get claps on the screen or something. Also, a thank you to Victoria Coates, BHS Secretary, for setting this up, and to Will and Liv for hosting today. And I will hand you back to them to close the webinar. Thank you.
Brilliant. Thanks, Helen. Yeah, just to reflect on that, really interesting talks all around, and thank you again for coming to present today. As I mentioned, this recording of this webinar and these presentations is going to be available on the BHS websites in probably towards the end of the week. So keep an eye out for that. Thank you very much.